So good evening. So today we will see the problem solving session 12 on chapter 12, week 12 on the chapter crystallizations. Here is a brief recap of this chapter: crystallization, the type of crystal geometries, the solid liquid phase equilibrium, theory of crystallization, design of crystallizers, crystallization equipment. So starting from the MCQ questions, question first is what is meant by the crystallization? So crystallization is a process of solidification of atoms into the highly structured forms. So here the solid liquid separation and purification techniques. When the mass transfer occurs from the liquid solution to pure solid crystalline stage. So option B is correct. A question to you: is crystallization a chemical change? So crystallization is a physical change. So there is a no product form because like mixing up A plus B form the others. So here only the crystal forms. So therefore the crystallization is a physical change. So this statement is a false. Question 3: which of the following condition is necessary for a crystallization to occur from a solution? Option generally to for the necessary condition for the crystallization, the solution must be the supersaturated. Means concentration of salt exceed its solubility limit. So in this case, the excess solute begins to crystallize out of the solutions. So the solution must be supersaturated is necessary for the crystallization of solution. Into the question number, what role does agitation play in a crystallization process? Generally, we know the agitation helps the mass transfer and also others like preventing the settlings. So here we can check the options. So B is like man. So you know the purpose of the agitation in the mixing process. So in the mass transfer from solid to the liquid solution to the solids and prevent the settlings. Moving to the question number 5. Why is a supersaturated solution unstable? Supersaturated means the concentration is higher, means the concentration is exceed, then it's a solubility. So concentration is higher than the equilibrium, so there is a then the instability, right? It's a simple, just this question is based on the simple concepts. Question 6: which of the following is not a common type of a crystal geometry? So option you have to select the option. So generally the crystal geometry are like cubic, tetragonal, triclinic, rhombohedral, then monoclinic. But here is a D is a not a type of the crystal geometry. So it is like a spherical shape. You can say here is a spherical. We can say the like any crystal like spherical as so on. But the geometry is the geometry. So spherical not included in the geometry. So it included the shape. So we can say like spherical, then like other like nano rod, nanotubes, nanoflakes, etc. Question 7: in a solid liquid phase equilibrium, the system is said to be equilibrium when? Check the option. The solid is completely dissolved in the liquid. No. Here is a solid liquid phase equilibrium. So it means in both phase the concentration should be remain constant, like in the solid and liquid. So this is not. This is also not because here a solid is completely dissolved in solid means a single phase. So here is a not maintained. It is a not a equilibrium. So there is a no exchange of heat between the solid and liquid. This is not the rate of solidification equal to the rate of melting. This is so the rate of solidifications equal to the rate of melting. So ensuring that the amount of solid and liquid phase remain a constant. Right? Option C is correct. Question 8. Which of the following best describe the process of the nucleation in a crystallization? In a crystallization, there are the process how to occur the crystallization. Initially, the supersaturation, then nucleation, then crystal growth. So here is a which of the following best describe the process of the nucleation, right? Formation solid particle directly from the liquid. No. So here like step like supersaturation means this process involved in the crystallization, then nucleation, then crystal growth. So here from the liquid, this is not describe the process of the nucleation and growth of the crystal from the pre-existing solid surface. No, this is not. So initial formation of small solid particles from the supersaturated solution. This is possible solutions. Rapid cooling of the solution to form the crystal. No, because here we have to maintain the supersaturation so means condition in the crystallization. So it means primary. It is a critical factors in a crystallization. So initial formation of small particle from the supersaturated solution. So this is the best describe the process of the nucleation in crystallization. Going to the question number 9. Which type of crystallizer is commonly used for the large scale production in the chemical industry? Batch crystallizer, fluidized bed crystallizer, Sense one Valka crystallizer, D is a evaporative crystallization. So general evaporative crystallizer used for a large scale production. So it in this process, so it operate by concentration of solution to the evaporation, leading to the supersaturation and subsequent the crystallization. So mostly, so this evaporative crystallizer used for the large scale production. Question number 2: which of the following factor is least likely to affect the crystal growth rate during the crystallization? So this supersaturation level also affect the crystal growth, temperature, agitation days, and color of the crystal. So this is a not affect. Means all these factors affect the crystal growth in a crystallization. Question number 11. In the design of the crystallization, which parameter is critical for the maintaining proper supersaturation? So cooling rate or evaporation rate? Solubility absolute no. Pressure inside the crystallizer no. Viscosity of solvent this is also not a critical. So cooling rate or evaporation rate. Uh, the critical parameter for maintain the proper supersaturations. Question number 12. The the area shape factor phi a of cube is given by, right? So phi a is a area shape factor, right? So here is the given the cube, right? So so first uh, to calculate the area shape factors, so AC means the area of crystals equal to phi a into a square, right? So phi a AC divided by a square, right? So we have to calculate this one. So here is the AC means area of cube. What is the area of cube? Like 6 a square is the side of cube, right? So put this value in these equations. So 6 a square by a, right? A square get cancelled. So it's a 6. So area shape factor phi of cube is 6. Option B. Moving to the question number 13, the volume shape factor phi v with a subscript upper sphere is given by, right? So similar equation you have to follow, like qv is equal to vc by d cube, right? So d is the diameter of the sphere, right? And the volume of vc of the sphere pi by 6 to d cube, right? So pi by 6 into d cube divided by d cube, right? So pi by 6 you calculated pi by 6 at 0.5235. Option C is correct one. Moving to the question number 14. What is the ratio of phi A divided by phi V for a cubical particle? Right. As last two questions, we calculated the area shape factors of the area and volumes. Right. So I can write down directly phi A is equal to SC by S square, right? Phi V equal to VC by A. Now for cube, the area of cube 6a square and volume of cube a cube, right? Just we have now take a ratio qa equal to qv, right? AC a square plus vc a cube, right? So put the value of area and volume in these equations. 6a square divided by a cube, get cancelled, right? It's a 6. Now question number 15, what is the ratio of phi v divided by phi a for a spherical particles? So it is just in the question 14, just phi a divided by phi v, now phi v by phi a, but here is a spherical particles, right? Right. Phi v phi a equal to vc spherical d cube AC d square, right? So area of a spherical is equal to pi d square, and VC is a pi by 6 d cube, right? So we see it pi by 6 into d cube by d cube divided by AC is a pi d square divided by d square. D square get cancelled, d cube get cancelled, pi get cancels. Now 1 by 6. So 1 by 6 is a calculated 0.16. Option B is correct. Question number 16. The characteristics length of particle increase from 1 mm to 1.1 mm when kept suspended in a solution of supersaturation level is 1.05 or 2 hours. If a particle of 0.8 mm size is allowed to grow in the same solution under the similar condition for a 4 hour, what would be the final size? Right. So here is a two case given. So we have to calculate the final. So first, from the first solution, we have to calculate the crystal growth rate, then that we have to use to find out the final ones, right? So here we have to use the Mac-Cabe-Del law, EMC Del law. Right? So G is equal to dl by dt, right? Okay, right. So here is only changing the particle length. Okay, okay, let the particle, right? So now so time is a particle is a fixed one. So in the case one, like G is equal to L2 minus L1 over T, right? So here is L2 1.1 minus 1, T is the time 2, right? So G is equal to 0.05 mm per hour, right? Now case 2, so initial size zero point 0.8, so we have to calculate the L2 size, right? So G is equal to L2 minus L1 divided by T, right? So GT, simplify this equation, this relations L2, L1, right? So here you have to calculate the L2, right? So L2 is equal to GT plus L1, right? So here GT 0. Sorry, G is a crystal growth rate 0.05 into the here is a time given 4 hour 4 into L1 is a 0.8, right? So it's a 1 mm final size. Check the option. Option C is the correct one. Question number 17. The solubility of the sodium sulfate in the water at 25 degrees Celsius is a 30 gram 100 ml of water. Right here is the given solubility of sodium sulfate. If a 40 gram of sodium sulfate is dissolved in 100 ml of water at 40 degrees Celsius, then cooled up 25 degrees Celsius, then how much sodium sulfate will be crystallized out, right? So whatever in the supersaturation conditions, whatever the means the exceed the limit of the solubility, that can be crystallized, right? There is a simple phenomena, a simple concept we have to use, right? So solubility is a 30 gram 100 ml. Here is a 40, right? So amount, so super saturation means excess is equal to amount dissolved in the solubility at 25 degrees Celsius, right? So here is a 40, right? Amount dissolves and solubility is a 30. It's a 10 gram. So 10 gram of sodium sulfate will crystallize out from the solution. So remaining will be in the mother liquid. Remaining will be passed into the mother liquid. Question number 18. The freezing point of pure benzene is 5.5 degrees Celsius. A solution is prepared by dissolving 0.1 mole of non-volatile solute in a 1 kg of benzene, right? Mole divided kg means this is a molality, indicating the molality, which has a freezing point depression constant Kf is K of 5.12 degrees Celsius into kg per mole. What is the freezing point of the solution? So here we have to calculate the freezing point of the solution, right? The freezing point depression freezing point depression denoted by delta Tf equal to Kf. This is a freezing point depression constant into m. Here is a small m is a molality of the solution, right? Now, so here is the molality 0.5 mole per kg of benzene, right? 0.5 divided by 1 is the 0.5, right? So m value is 0.5 mole per kg, right? Now put in these equations. So Kf is a 5.12 into molality 0.5, right? 2.56 mole mole get cancels, kg get cancels, so it's a degree Celsius, right? So this is a freezing point depression. Now freezing points of solutions. Right. So 5.5 minus 2.56, right? 2.94 degrees Celsius. So this is the freezing point of the solution. Question number 19. A continuous crystallizer is designed to produce 1000 kg of crystal per day if the crystallizer has a volume 10 meter cube and density of slurry is 1200 kg per meter cube. Calculate the recitum times of the slurry in the crystallizer in hours. Right. 10 meter cube density of slurry given. Now we have to calculate the recitum times. So to calculate the resident times, like T is the resident times equal to volume of crystallizer divided by flow rate of the slurry. Right. Here the volume given. Now we have to calculate the first flow rate of the slurry. To calculate the flow rate of the slurry, right? So here is so here is a crystallizer produce the crystal 1000 kg of crystal per day, right? 1000 kg per day divided by density kg per meter cube, right? Kg get cancelled, so meter cube, but that's the flow rate. 0.833 meter cube per day. So convert day into the hours. It was 0.0347 meter cube per hour. Right. So right. Now put in these equations. So here is the volume of crystallizer 10 meter cube and flow rate of the slurry 0.0347, right? Meter cube per hour. Meter cube get cancels. It's a 288 hours. So 288 hours of resident times of a slurry in the crystallizer. Question number 20. In an experimental on a growth of sample, fairly uniform size particle L is equal to 1 mm in a supersaturated solution. It is found that the volume of particle increase at a rate of dVp divided by dt equal to 5.2 into 10 to the power minus 14 meter cube per second. Right. Determine the crystal growth rate if the volume shape factor is given. Right. Here is a relation given dv by dt means value given dv by dt. So we have to calculate the crystal growth rate. Right. Here is the L given 1 mm, right? So dv by given L 1 mm convert into the meters, like 1 into 10 to the power minus 3 meter. Right. Now Vp equal to 5V. Here is a volume shape factor given into L cube, right? Now differentiate these equations by dt. So dvp by dt equal to 3L square, right? 5V into d L by dt, right? As you know, the crystal growth rate G is equal to dl by dt, right? So this becomes a G. So G is equal to dvp by dt divided by 3l square into 5v. So all the value given here, so we have to put, right? 5.2 into 10 to the power minus 14, 3 into 1 into 10 to the power minus 3 square into 5 v 0.42, right? So 4.12 into 10 to the power minus 8, right? Take the unit meter cube second. Here is a 3, okay, real is a mm square, meter square, right? So meter second. This is a crystal growth. Going to the question number 21. An aqueous salt solution enter a crystallizer operating at steady state at 25 degrees Celsius. The feed temperature is 90 degrees Celsius, right? The salt concentration in a feed is a 48%. The salt crystallizes as a pentahydrate, right? 5s2. The crystal and mother's liquor leave the crystallization. The molecular weight of anhydrous salt is a 135, right? The solubility of a salt at 25 degrees Celsius is 20%, right? The feed flow rate required for the production rate of 100 kg per second of the hydrate salt in a kg per second. So we have to calculate the feed flow rate, right? So here is a crystallizer, here is a feed, here is a crystal, denote C, F, this is a mother liquor, denote F, right? So weight percent means salt concentration given, that is a X F 0.4, right? And molecular after 5 is to molecular weight of 5 is to O into 18 into 5 equal to the 90, right? Now weight, here is a after the anhydrate salts here. So we have to calculate the weight percent of the hydrate crystal. Weight percent of hydrate crystals after crystallization, right? 135 plus 135 plus, here is a pentahydrate, so it's a 90, 0.6. So Xc 0.6, right? Means weight of salt in a crystal, means after the crystallization. Now here is a mention that the solubility of the salt is a 25. So initially what is the solubility? Okay. So in the solubility of a salt at 25 degrees Celsius to 20, so it will be the same in a mother liquid, right? So XL is equal to 0.20. So we have to calculate the feed flow rate. Here is the 100 kg per second. Calculate to production rate of the 1000 kg of second of hydrate salt. So first we have to do the material balance of this unit OMB, overall material balance, F equal to L plus C, right? So here is a C is a 100, F is equal to L 100, right? So L equal to F minus 100. That is the equation number 1, right? Now take a solute balance and component balance, solute balance, right? F into weight fractions of salt in feed into L into XL C into XC, right? So either XF is a 0.4 into F, XL is a 0.20, sorry, here is a 0.20 into L, C 100 to 0.6, right? So here L equal to put this value in these equations. So 0.4 F equal to 0.20 into F minus 100 to 60, right? So now we calculate this. After calculating, we will get F is equal to 20 kg per second. So this is the feed flow required for the production rate of 1000 kg per second of the hydrate salt. Question number 21. An aqueous salt solution enters the crystallizer operating at steady state at 25 degrees Celsius. The feed temperature is 90 degrees Celsius. Okay, this is the same one. Question number 22. 1000 kg of solution containing 50% by weight of salt dissolved in it cooled, and 400 kg of anhydride salt is separated out. That's a C, right? The solubility of salt at a lower temperature in kg per 100 kg of water each, right? So 50% of wet salt dissolve, right? So it means 500 kg of salt in a feed, right? And 400 kg of salt in a product. So it means that 100 kg salt in the mother liquid. So here 500 kg of salt in a feed. So 500 kg of water in a feed. H2O in a feed, which is equal to 500 of kg of water in a liquid, mother liquid. Will be the same. H2O in a mother liquid, right? So here in a mother liquid, 100 kg of salt in a mother liquid. So 1000 kg of salt is soluble in a 500 kg of water, right? Then, but in this question asks solubility of salt at a lower temperature in kg of 1000 kg of water. So in the question asks like x kg of salt is soluble in 100 kg of H2, right? So x is equal to 100. Right. So here is a 100 kg of water. So 20 kg of salt divided by 1000 kg of H2. Here is a simple like 1000 kg 1000 kg of salt is soluble in the 500. So far in the and question asked 100, so it's a 20. Right. Question number 23. 35 8% of N2SO4 solution in a water initially at 50 degrees Celsius is fed to the crystallizer at 20 degrees Celsius. The product stream contains a hydrate crystal into SO4 10 H2O is equilibrium with the 28% of the N2SO4 solution. Right. The molecular weight of N2SO4 and N2SO4 10H2 are 142 and 322 respectively. The feed rate of the 35 8% solution required to produce 500 kg per hour of the hydrate crystal in kg per hour. Right. So here you have to calculate the feed rate, right? So here is a C, just C given 500 kg per hour. Yep, C, yeah, C given, right? Kg per hour, right? Now here in the solution, the accept 0.35 and 28% of inactive means that's a XL. Means mole fraction of the Na2SO4 in a mother liquid is a 0.20, right? Now we have to calculate the XC. So to calculate the XC, equal to 142 solution 322, right? So 0.44, 0.44. So first take overall material balance OMB equal to F equal to 500 plus C plus L, C plus L 500 plus F, right? So L is equal to F minus 500. Now take a solute balance. F x F equal to C L x L. 0.35 F equal to 500 into 0.44 plus L. F L write down this means F minus 500 into 0.20. Right. After calculating, so F is 800 kg per second. So feed rate is 800 kg per second feed into the crystallization to produce the 500 kg of hydrate crystals. Into the question number 24. Na2SO4 10S2 crystal are formed by cooling 100 kg of 30% by weight aqueous solution of Na2SO4. The final concentration of solute in the solution is 10 weight percent. Then weight of the crystals. So it's similar questions, but here you have to calculate the C, right? So here is a weight percent 30%. So that's a XF 0.30, right? XC is 0.44 is 142. Molecular rate of Na2SO4 divided by this one Na2SO4 plus 10 to 0.44, and XL is a 10%. Right? X you have to calculate. First take OMB. F is equal to C plus L. F given 100, C unknown, L unknown. So L is equal to 100 minus C. Right? Equation 1. Now take a solute balance. L X F, sorry, feed F C X C plus L X L. F is a thousands, X F is 0.30, and C X is a 0.44 plus L is a 100 minus C into 0.10. So C is a 58.82 kg. So put in these equations in the first, then you can also calculate the weight of the mother liquid. And MSMPR, it means mixed suspension Mixed product removal crystallizes up 5-meter cube vacuum balloon. Produces crystal of mass average particle size is 1 mm. If the product stream is withdrawn at a rate of 4-meter cube per hour, calculate the crystal growth rate and the rate of the secondary nucleations denoted by B naught. The magma density is 150 kg per meter cube and true density of crystal is 1900 kg per meter cube. Thus, volume shape factor is a 0.6. So here we have to calculate the crystal growth rate and the rate of the secondary nucleation. Okay. Here is the MT given, volume shape factor given, volume given, crystal mass average particle size is 1 mm given, right? Mass average crystal size denoted by LM the bar, right? So the 3 square root 6, right? It's cube root into G to tau, right? Here G is a crystal growth rate and tau is a resetting time, means holding time. So Lm is a 1 mm given. Take these terms here. You can write down directly 6 1 by cube into G into tau, right? So after calculating 0.55 mm. Now we have to calculate the holding time. Right? So V by flow rate. Right? Here is the volume 5 and flow rate 4. So 1.25 hour. Now we have to calculate the crystal growth rate. G is equal to 0.55 divided by 1.25. So our convert into the seconds. So 3600. Now this is 0.55 convert into the meter 10 to the power minus 3. Right? So 1.22 into 10 to the power minus 7 meter per second. Right. So first we calculate the crystal growth rate. Now we have to calculate the rate of the secondary nucleation, that is the P naught. Right. Now second part, the total mass of crystal per unit suspension volume is given by MT. Here is MT is the magma density 6 into 5V volume shape factor into density of crystal into N naught. N naught is the population density of a crystal having a very small size into G into tau raised to the power 4, right? So here from this relation we have to calculate valency factor given, density given, magma density also given. All we know, so we have to calculate this one, the population density. In 0 point, we can also say 0 point population density, right? So n naught equal to, after put all the value here, it will get the value 2.4 into 10 to the power 11 nuclei per meter 4, right? This is a 0 point size, 0 size population density, right? Now we have to calculate secondary nucleation, because this would help to calculate the secondary nucleation rate. Secondary nucleation rate B naught equal to N naught into crystal growth rate, right? So it is a 2.4 into 10 to the power 11 into G. We calculated 1.22 into 10 to the power minus 7, right? Meter per seconds unit. So 2.99 into 10 to the power 4 nuclei per meter cube into second. So this is the rate of secondary nucleations. So I covered all the question based on this topic included in these chapters. So thank you. So we will meet next Friday. Okay, thank you all.